Hello everyone and welcome back to this course. So last class we discussed about different flow field designs such as serpentine flow field and interdigitated and the parallel flow field design, wherein we saw how this flow designs basically influence this mass transport and how they can be brought into picture depending upon what we are dealing with. So moving on, let's start with a new section, that is scale up issues. So far what we have seen is, in case of fuel cell, we have seen typically three losses. There is activation over potential, then we have seen ohmic as well as mass transport. Same thing is also applicable in case of electrolyzer. We have activation over potential, ohmic and mass transport. This is E operating, Z, this is J and E. So this is E OCV. So the question arises is, even if we have let us say same material, so let us take two case studies. One is let us say 25 centimeter square. We have discussed this before. So this is let us say 25 centimeter square cell and this is let us say 300 centimeter square cell. So this means the area of the electrode, and we have seen this, that there is a difference in the performances as and when the cell is scaled up. So let me show this structurally, schematically. This is 25 centimeter square and this is 300 centimeter square. This is length and width. So this entire area is 300 centimeter square. So length into width, this is length into width, this is 25 centimeter square. So we have seen that the cell with a smaller electrode area performs better with respect to the cell having higher electrode area, and if we normalize this with respect to current density, and this is what we get. So question arises is, why isn't the performance of fuel cells same or at least similar, let me write similar, with respect to current density as the size of the cell is increased So this is what is all about the scale up issues. Despite keeping all the rest of the things constant, such as the, let us say, manufacturing of the bipolar plates is same, the design of flow field channel is same, the catalyst is also, let us say, same in the both of the cells, even the GDL is same, and even if we keep all these things constant, even if the clamping pressure is also same or similar, still we will have these differences in the performance that is basically attributed towards the scale up issues. And if we chart down this scale up issues, basically one of them has already been discussed. First one is basically thermal management or thermal issue, we can say. Second is again the water management or water issue. How well is the water managed in the cell? Third one is your contact resistance. We have discussed this before. And there are a few more issues, but I am here highlighting only 3 important ones. So let us first understand what the scale up issue is. So what is scale up issue? why is it so serious, or why is it become so important when the cell size is increased? So let's take an example. Let's take example of class of, let's say, 10 students. Okay. So when I have 10 students, it's very easy for me to handle the class. So let me write this is it's relatively easy for teacher to handle the class. The teacher can also coordinate very effectively with each and every student. However, if I have class in which we have, let's say, 100 students or even more, then it becomes more chaotic, right? Chaotic. So the reason it becomes chaotic, because the size of the class has increased, and it also becomes difficult, basically difficult for the teacher to handle the class. And obviously, it's even difficult for the teacher to even coordinate with each and every student. The reason is because it is more chaotic in nature. Similarly, if we extend this thought with respect to the scale-up issues, we can see that similarly, let me write this. Similarly, when the size of electrode increases, some inevitable issues are incurred. So even if the size of the electrode is increased, or we have more cells in the stack, all these things lead to scale-up issues. And as we have seen before, we have three issues, mainly three issues. One is your thermal issue or thermal management. Then we have water issue or water management. And then third is your contact resistance. It's basically the contact between the electrode and bipolar plate, and that is what leads to the contact resistance. So let's first discuss about the thermal issue or thermal management. So let me take an example again. So let's say if you are operating, if we have a small cell, say 25, say 5 centimeter square, this is the area, and its producing output is electrical output. This is electrical output is, let's say, around 5 watt. And if the efficiency is, let's say, 50%, then we have thermal output as well, and the thermal output is also around 5 watt, as the rest 50% in terms of efficiency is released as a heat. Now this 5 watt is not a considerable amount of heat, as the size of the cell is small. So this 5 watt heat that is released is not that significant, and that is why we can neglect this heat that is released from the system. However, let's say we have now second example. This was the, let's say, this is the first example, example 1, and this is example 2. Increasing the power output of the cell, let's say we have 1 kilowatt fuel cell stack. Okay. So, 1 kilowatt fuel cell stack, the efficiency is around, let us say 50%. Let us take the same numbers, and if the 50% is the efficiency and the electrical output is 1 kilowatt, which means the thermal output is also around 1 kilowatt. Now, this is a considerable heat, and if you do not pay this attention to this heat that is released from the fuel cell stack, then there will be issues. Now, this thermal output that is around 1 kilowatt is quite significant, and therefore needs to pay the attention. So, what if this heat is not given that attention, or it is not given that significance? What happens is, let me show it graphically or schematically. So, let us take, this is the electrolyte. Now, this is the commercial, let us say Nafion membrane we have taken, or any electrolyte or membrane which has this dependence on the water intake. This is hydrogen and oxygen. We know this is the proton transfer from anode to cathode. So, we have taken the membrane which depends on the water intake, or that depends on what is the water available in the electrolyte. If we have more water available, this water basically acts like a carrier for proton transfer from anode to cathode. So, this specialty is basically it carries proton using water molecules, right. The audience can refer to the proton transfer through this Nafion membrane separately. So, what happens is, as the temperature increases, so please remember that we are now not paying attention to the heat that is released, and that is why the temperature of the stack here is increasing. So, as the temperature is increasing, so water that is available in the electrolyte or the membrane, basically it starts evaporating, and in other words, the electrolyte starts losing the water content, and if that happens, the water is not available anymore for the proton conduction, and if the water is not available, protons will not be moved, or protons will not be transferred from anode to cathode, and in that sense the electrolyte or the membrane in this case acts just like an insulator. So, that is why you can say that we have to maintain the water in the electrode and the electrolyte particularly, and in order to do that, we have to also maintain the temperature of this cell or the stack, and that is why this thermal management of fuel cell comes into picture. Typically that employs an electrolyte which depends on the water intake in terms of its proton conductivity. So, let me write this up. So, electrolyte may not be available for proton conduction, and that implies this electrolyte. So, when I say electrolyte may not be available, in other words, it is not available as a proton conducting material. Electrolyte will not be able to transfer the protons H plus. So, that implies this electrolyte is acts as an insulator for the protons, and that is why it is very important to control and manage the heat that is liberated from the fuel cells. And for that, so let me write, therefore heat released by the fuel cells needs to be managed, and that is why coolant and coolant designs or flow designs are basically employed. Therefore, coolant and cooling channels are employed. So, what basically is done is, let us say we have, this is the bipolar plate, or let us take the monopolar plate for simplicity, and then we have this channel designs for, this is for, let us say this is H2 in and H2 out. So, if you look at this, the other side, how it basically has is, basically we have the coolant designs on the other side. So, it is the same monopolar plate. I am just showing the other side of the other face of the monopolar plate, and then here we have, you can say, coolant designs. Basically these are the coolant channels, and they also take the coolant in and out. So, this is coolant in, this is coolant out. Let me write coolant in and coolant out. Typically in case of low temperature fuel cells, distilled water is used as a coolant. Some oils or some other modified coolants are also used for better heat transfer from the fuel cell. Let us move to the second case, that is water management. So, let me write this up as the area of fuel cell increases, what happens is the more reaction sites are made available. So, more reaction sites are made available. So, as we know, if the reaction sites increase, in other words, we have more number of reactions occurring per unit time. So, we can say this is more number of reactions per unit time will also increase, and that basically, although it generates more current, however, this more reaction sites will also increase the water production. So, water production also increases. So, if we recollect, if you are just talking about hydrogen oxygen fuel cell having an electrolyte that conducts protons. So, proton transfer, and this is, let us say, anode and cathode. So, if we know that water gets produced on the cathode side at the catalyst layer here. So, this is the catalyst layer, or we can say triple phase boundary. So, we can see that this water gets produced on the cathode side. So, if the water is not taken out instantly, in other words, so if we have water produced here, so we have this O2 coming in, and this is H2. So, O2 comes out and unused oxygen plus water comes out on the cathode side. So, this water which gets produced at the catalyst layer, if it is not taken out instantly, what happens is it blocks the pores of GDL. In other words, the water gets stuck at the catalyst layer and in the diffusion layer. So, once that happens, the oxygen that is supplied to the fuel cell is not able to reach the catalyst layer on the cathode side, and that is why it is, in other words, basically we are not supplying the oxygen to the fuel cell, which basically brings the issue of mass transport issues. So, that is why the cell ends up in the mass transport losses, and that is why this water that is produced in the fuel cell has to be taken out every instant of time. So, let me write this up. So, it blocks the pores of GDL. So, that implies oxygen will not be able to reach the reaction site, or we can say catalyst layer, or I can say the cathode. And where does this lead to? This is a reaction rate. Since we are not supplying the oxidant, the second half reaction which is happening on the cathode side will not take place. So, the reaction rate will be decreased drastically, and that is why, or in other words, this mass transport losses will be increased. So, basically, we need to take this water out all the time, so that those pores of gas diffusion layer, they are made available for the oxygen flow in and out, and if that happens, then and then only the reaction that is occurring on the cathode side will be effective in terms of the happening, and that is when the cell will start or continue to produce the power. If that does not happen, if the water gets stuck by due to some unforeseen reasons, the oxygen does not reach the cathode or the reaction sites, and the reaction will not take place, which we know that is protons and electrons combining with oxygen to form the product water on the cathode side will not take place. So, if the half cell reaction does not occur, the complete cell reaction will not be complete, and that is why the cell ends up in the mass transport losses. So, if we try to draw this schematically, let us say this is the electrode area, and this is the, let me draw this with these are the channels. So, I have taken the serpentine channels. So, this is the out and this is the in. So, I have particularly shown only the cathode. So, when we have the oxygen in, so as and when the oxygen starts flowing in those channels and it reaches the catalyst site, the water instantaneously starts producing, or it gets produced. So, we have small collection of water as and when the oxygen travels. However, with the more flow of oxygen, you can see that there is more water being generated. So, typically we have more water here in the second half, of the cell, and as we have more water here at the in the lower half of the cell, it ultimately basically blocks the oxygen supply, and that is why we can see that here the mass transport losses will be more typically in terms of oxygen supply, typically in the lower half of the cell. So, let me write this up. So, water quantity increases as and when oxygen passes through the channels, and this water gets accumulated as and when the oxygen travels, and once it gets accumulated, it starts basically, it is an hindrance to the oxygen supply to the catalyst site, and that is why the performance drops. So, in other words, the performance of fuel cell decreases. So, what are the different ways how we can mitigate this problem? So, one thing is we need to understand this problem cannot be eliminated, because if there is a reaction happening, there is a water production, and this water production will effectively give rise to mass transport losses if not paid attention. So, we have to basically flush this water out of the system at regular intervals of time, so that this mass transport losses are not incurred in the system. And the last issue that we have already discussed, basically, that is the contact resistance. We have already touched upon this, discussed in detail. Let me quickly go through it one more time. So, what happens is basically, as the size of the cell is increased, let me only show on the one side. So, as you can see, this is where we have the electrode and the bipolar plate interaction. So, this is our GDL, and this is the bipolar plate. So, this is where the contact is, or let me write, this is an interfacial contact between bipolar plate and the GDL. Okay, and of course, as the size will increase, we will have more of such contacts. What basically happens, as we have discussed this before, when the size of the cell increases, the contact pressure at this interface is not very uniform. In other words, at some locations, the contact between these two materials or components will be more. At some places, this contact pressure will be less, and if we try to look at this contact resistance, interfacial contact resistance with respect to contact pressure, this goes exponentially down. So, in other words, if the contact is better between these two components, that is gas diffusion layer and the bipolar plate, we will have a very low contact resistance at this particular interface. And this problem is, again, as I said, it is an inevitable. When we increase the size of the cell, we are expected, or we can definitely expect at some locations a poor contact and at some locations a good contact. So, on an average, this contact pressure is not very uniform, and since it is not uniform, we can end up at the different contact resistances on this electrode area, and that is what leads to higher contact resistance in terms of poor performance as and when the size of the cell is increased. So, with that, we come to an end of the section on the scale-up issues. Thank you everyone for listening, and next sessions will be handled by the Professor Pratham Arora. Thank you.